Alright, so today we're looking at relations, functions, and graphs. So we're going to be basically focusing on the relations and functions aspect of it. We want to identify the ways of presenting relations. What are the ways of presenting relations? We want to understand what makes a function a function. We want to understand the types of relations. And then from those types of relations, understand which types make functions. And then we want to talk about composite functions. So what are composite functions? How do we solve them? Alright, so relation, this shows how two sets of data are connected to each other. So for instance, you have two people. You may have your mom and yourself. So it's mother, son, mother, daughter. That is a relation between two individuals. Likewise, when we have data in maths, we refer to them as having a relation. So the relation of one relative to a next. So the relation part of it shows how they both are connected to each other. Now we got ways of representing relations. So the first one is what we refer to as a set of ordered pairs. So a set of ordered pairs. So for example, that would be like having 0, 0, 1, 2, 2, 4, 3, 6. So these represent a set of ordered pairs. A set of ordered pairs. So basically these are like coordinates. They are like coordinates. Now we could represent this as well using an algebraic expression. So if you notice here, just to go on this part of it, so if you notice here, this is like the input. This represents the x part of it, and this part represents the y part of it. So algebraically, we often write it like this. Fx is equal to 2x. So this here represents the input, and what comes out, whatever answer you get when we use this formula, represents the output. Another way of writing this is also like this. So x maps to 2x. Now if you compare this here, essentially our input for this first one represents the x values. So if we were to use this in a formula here for these ones, let's say x is equal to 0 as we see here. So x equal to 0, and we use it in this algebraic expression here, we would say that the input 0 is equal to 2 times x now being 0. So therefore, for the input 0, our answer is 0. Okay, so f of 0, or the output of this, is essentially the same thing as having y. So as you can see here, this represents the coordinate here. So that's how we got the 0, 0 here. Now, let's try it for the input of 1. So x is equal to 1. So we are using 1 as the input. So when we use that into this formula again, we will get 2 times 1. So for an input of 1, you would get 2 as the output. Or in other words, y is technically equal to 2 if we were to write it as a set of ordered pairs. So essentially the coordinate is 1, 2, which we have here. And if we do these for these other two here, we will get the same output. So if we insert 2, we will get 4. If we insert 3, we will get 6. So based on this process here, you will realize that these set of ordered pairs are connected to this algebraic expression. Now these are the numerical representations of it, right? So now these two kind of gives us a picture of this setup. So for instance, arrow diagrams. We have the input, so these values that you saw here essentially represent the input, so 0, 1, 2, and 3. So then now we have our output, which we saw here. So the input was these first values of x's, and our outputs, basically these. Once put into this, gives us this, would essentially be 0, 2, 4, 6. So in essence, 0 is mapped to 0, 1 is mapped to 2, 2 is mapped to 4, and 3 is mapped to 6. Alright, so this here is what we refer to as an arrow diagram. And of course, we could also represent it graphically. So on this axis, being the x-axis, represents the input, our x. This here is our input. And we have what comes out of fx, or what we refer to as a y-axis. This gives us our output. So now, if we were to plot this, we're using these same points. So 0, 0, 1, 2. So 1 on the x-axis, then 2 on the y, then 2, 4, 2 on the axis, then 4, then 3, 6, so 3 here, and then 6. This right here represents our graphical representation of this relation here. So as we can see, we have the set of ordered pairs, very important, set of ordered pairs, arrow diagrams, algebraically and graphically. These are the 4 ways of representing relations. All right, so take this down, and then after we look at the next phase. All right, so we have types of relations. So one to one, many to one to many, and many to many. So one to one. So one to one typically looks like this. So we have some inputs over here, and our outputs, they typically match literally one to one. So for every input, we have a single output. So none of the inputs share an output. Okay, they all have the unique outputs. So this here is one to one. Now, many to one, there are times that they may share outputs. So for instance, this input has this output, and this input here can also have this output. Likewise over here, this input has this output, and this input here also has that output as well. But in that same instance, we could also have a situation where there's only one going to one output, okay? So when we do our activity, you'll notice that when we do a particular arrow diagram for a certain function, you would get an answer similar to this, all right? So we refer to this as a one-to-one. This one is a many to one. Now, the one to many is kind of the reverse of this. So in essence, you would have an input going to two outputs. Likewise here, this input shares two outputs. And then we could have a situation where only one is shared here, all right? So that's our one to many. Notice how it's branching out from one to two. That's why we say many. We don't care if it's 2, 3, 4, or 5. Once it's 2 or more, we refer to it as many. Likewise here, we have 2 going to 1. Instead of saying a 2 to 1 relation, we say a many to 1. All right. And notice in this case, the dominant one is a many to 1. So even though we have something that looks like a 1 to 1 here, because the primary ones that we see are many to 1, it supersedes this single one. Likewise, to this instance here, we see a situation where we have one going to many, one going to many. Once we have the many involved, it supersedes this. Okay, now the many to many is literally a combination of 2 and 3. So just so you can see it, I'll change the colors so you could see the different aspects. So let's say these are going to each other here, and let's say we also have this one. Notice here in this situation, we have 2 here going to 1, which gives us the many to 1 effect. But likewise, we also have a 1 going to many, which gives us the many effect. So as a result of that, this is why we do it from this perspective. This is why we call it many to many. So take this one down and we'll continue from there. All right, so based on what we did so far, what are the ways of representing relations? What are the ways of representing relations?
There is set of order pairs.
Wonderful.
Algebraically.
Algebraically, lovely.
Graphically, and arrow diagrams.
Lovely. All right. All right, so we're gonna use this to bring home the concept of these things here. And we're gonna use this arrow diagram to basically explain the concepts of domain, codomain, range, and image. So as we know, this first part represents our input. So this is our input, and this here represents our output. So the first thing, domain. So domain refers to the input data. Now based on this, what is our input data?
1, 2, 3, and 4.
Lovely. 1, 2, 3, and 4. So we know that the domain is 1, 2, 3, and 4. Now, as it relates to the codomain, this refers to the possible outputs. So in this case, let's say we were looking at numbers from 1 to 10. That's our possible outputs that we have for this particular function. But it's like we have a cap on that, okay? So it's just 1 to 10. So we're just looking for the possible outputs on this side. So this side shows us all the possible outputs that we were looking at. So 1 to 10. The range refers to the outputs obtained from the inputs. So based off of that information, what do you think our range would be?
1 would be 3.
3. Yep.
3, 5, 7, and 9.
Excellent. 3, 5, 7, and 9. So for these particular inputs, these were the outputs that we got: 3, 5, 7, and 9. So those would be our range. Now, how did we get these outputs? So basically, this is a function here. So we're using these inputs inside of this function. So in essence, every value for x, we put it in this formula and we got an output. So for instance, 1. If we was to put 1 into this formula, we would have 1 being our input. So that would be 2 times 1 plus 1. So 2 times 1 is 2 plus 1 gives us 3. So for an input of 1, we get an output of 3. Now, if we did that for input of 2, so it would be 2 times 2, because that's our input, plus 1. So 2 times 2 is 4, plus 1 is 5. So for input of 2, we have an output of 5, and we did this for all the rest. So this was basically done for all these here, which is why we have these. It was done for all these here, that's why we have these particular outputs. So we're going to get into depth with this part of the functions in a bit, but now we're just understanding the theoretical aspect of this topic. So now the image. So for the image, that basically refers to a particular output for a specific input. So for example, 2 here is our input, so the image of 2 is 5. The image of 2 is 5. So because the input is 2, the image is 5. Who can tell me what the image of 4 is?
9.
Excellent. So the image of 4 is 9. So I'll let you all take this down and then we'll get into the functions aspect of this topic. Alright, so as it relates to functions, a function, it has one output for a specific input. Okay, so in other words, one input cannot produce 2 or more outputs. So as a result of that, a function is either one-to-one or many-to-one. So we have here the types of relations: one-to-one, many-to-one, one to many, many to many. Out of these 2 here are the ones that represent functions. All right, so these here are functions, one to one or many to one. As you would look at this, we see that no matter what we insert, we only get one particular output. Okay, so if you look at this, even though we have 2 going to this one produces one output, and this one produces one output as well. Even though it's a shared output, they both produce one output. Likewise with here, we have one input producing one output. Now if you look at the flip side here, we have one input producing 2 outputs. Okay, so that's a problem here. So this is why these 2 here are not functions, because one input produces multiple outputs, whereas as for a function, the outputs are unique. Okay, so we can only get one output from a particular input. So typically, as we would have seen from the algebraic expression, a function can be written looking something like this. So you could have f of x, where x is the input, and then we have the formula or the algebraic expression here that gives us the output. So once we insert the input, this would allow us to calculate the output. Now this is oftentimes written like this, so don't let that scare you when you see it written like this. So it's either one or the other. Okay, now in terms of plotting graphs, as we would have seen earlier, this here, okay, is the input x, and our output, which is usually expressed as fx, is the same way how we usually write it as y. So y equal 3x plus 2. So we put the input of x here, and then the outcome, which would be the y, essentially would give us our coordinate. Our input would be the x coordinate, and our answer would be the y coordinate. So then we would have our coordinates, and a couple of them together would give us a set of ordered pairs. All right, so composite function now. So composite function is a combination of 2 or more functions where the output of one function becomes the input for another. So for instance, we may have a function, and don't worry, we'll be going through all of this, the practical part of it. We're just trying to understand the theory behind this right now. We may have 2 functions, f and g. So as you can see here, this here is the g function, which goes inside of f. So we'll break that down and what that means later on. Can also be like this as well too. One thing I want you to take note of is when we have anything written like this, f to the power of 2x, this does not mean square the function. This does not mean square the function. It is the same as having it like this. Okay, so this here is another way of writing this. Likewise, if I have g squared x is the same as gx. So we'll explain what this means in a bit, but we'll start with the basic function aspect of things. So take this down and then we get straight into the examples of functions, how to work out the images of particular inputs and so forth. So let's just say that we had 2 functions. So we had this function f of x, which is equal to 2x plus 3, okay? So the first thing, I want to figure out what the answer would be if my input was 4. Now, if my input is 4, I have to insert it into this formula. So wherever I see the value of x, I will substitute it with 4. So for instance, now I would say 2 must be multiplied to 4, okay, because 2x means 2 times 4, and then I add 3 to that. So 2 times 4 is 8. Now 8 plus 3 is 11. So my answer is 11. So for the input 4, my image is 11, or in other words, my input is 4 and my output is 11. All right, so the next way again, similarly, if we had a negative number, so let's say we had negative 2, it would be the same concept. We still put the input as negative 2, so wherever we see x, we replace x with negative 2. So I would have here 2, then what would I do next?
In brackets, negative 2.
Negative 2, then what else?
Add 3.
Plus 3. Good. So what's 2 times negative 2? What's 2 times negative 2?
Negative 4.
Negative 4. Remember, positive times a negative gives us a negative. So negative 4 plus 3, and our final answer would be, what would our final answer be?
1.
What kind of 1?
Negative.
Alright, so negative 1. Good. So our input is negative 2 for this function, and our output is negative 1. Now, there are often ways that we can have this written as well. So for instance, they can give us a question that goes like this. So gx is equal to, let's say, 3x minus 1. And then after, it might say where x is an element of, so this fancy thing here means element of. So in essence, it's telling you all the numbers listed there. So the element of 1, 2, and 3. Okay, so what this wants you to do is to figure out what the input would be for all 3. Okay, so if I want to figure out what the input is, the output is for all 3 of these inputs, I would have to do them one by one. All right, so I want you guys to try this. I'll do the first one. So the first one, we have G, the input is 1. I would expect it to be 3 times 1, because that's what we have, minus 1. So then we'll have 3 times 3 is 1, take away 1 is equal to 2. Okay, what would be the next one we do? G as an input with 2 as an input, and then G 3. All right, so I want y'all to walk this down just to get a practice for this, and then we'll explore different functions that the input or the value or the variable x appears more than once. So try these two, and then after we'll move on to the next level. All right, what y'all get?
5 and 8.
5 and 8. So basically, 2 is the input for this. So we'll end up with 3 times 2. 3 multiplied by 2, subtract 1. So 3 times 2 is 6, minus 1 equal 5. So our answer here is 5. So this one here now, our input is 3. So then we say 3 times 3 minus 1, which is equal to 9, take away 1, which is 8. All right, so this time we want to look at functions that have the variable appearing multiple times, okay? And in one of them, we'll have it just looking a little different to the regular setup. Okay, so one here, this one is gonna be x squared plus 3x. And then we're gonna have h, which is equal to 2x minus 1 over x plus 1, and then we'll have a next one that we'll call fx, which is 3 minus 2x. Okay. In fact, let's write this one different. This one we write it different, how it's written, the second alternative, so how it can be written like this, 3 minus 2x. However, this is the same concept. All right, so first one we want to look at. All right, so the first one in this section, we want to look at G with an input of 2. Now, with this here, it's the same process. We need to put 2 inside of the formula. Everywhere we see x, we just replace it with 2. So if you see here, the input is x. So wherever x is, we are replacing that value of x with 2. So with that being said, we can say x squared, in this case, is going to be 2 squared plus 3 multiplied by 2. So then we'll end up with 2 squared, which is the same as saying 2 times 2. 2 squared just means 2 multiplied by 2, which is 4, plus 3 times 2, which is 6, and that gives me 10. Okay, that gives me 10. So that was for this function here. Okay, so notice that I had a value of x that I had to substitute in two different locations because x appeared in two different locations. Now we have another one here that appears in two different locations as well. I'm going to show you here that we have to apply the same principle. So let's make things interesting, and I'm going to use a negative value. So negative 4. All right. So what do you think I'm going to do here? I'm going to have what? 2. Then what's next?
Multiply it by -4.
Excellent. 2 times -4. Then what's after that?
You put it on the bottom with x plus 1. Replace the x with -4.
Are we missing something?
Oh, subtract 1.
Subtract 1, and then we go over
-4.
-4. So we are replacing this x with -4 because -4 is our input now. What's next?
Then we add 1.
Then we add 1. Now, what do we do now?
We multiply 2 by -4.
Excellent. So 2 times -4, a positive times a negative, gives us -8. And we subtract 1. So we're keeping with the same program. And then we have -4 plus 1. So essentially, -8 take away 1 will give us -9. And that will go over -4 plus 1, which is -3. So -4 plus 1 is -3. Now, usually, if I'm doing this and it gives me a fraction, I would leave the answer as a fraction. However, what I notice here is that 3 can go into 9 equally without a remainder. So as a result, I'm going to put a whole number. So -9 divided by -3, since we're doing negative divided by a negative, we get a positive. So 9 divided by 3 would give us a 3. Therefore, our answer would be positive 3. Okay, now just for this one here, we could have f, let's say we have -7. All right, so although this is written this way, it still has the same principle as these. Okay, so in essence, even though this is written this way, it still means f with the input x, which gives us 3 minus 2x. It's the same concept. So what we would have to do in this case is the same principle. We say 3 minus 2 multiplied by -7. Okay, now when I'm looking at this, I'm looking at this as 3 and I'm keeping this here almost as a separate situation. So just to give you an idea of what I mean, let's say we took this out and I'm just left with this minus 2x times -7. Okay, so I don't want to put back the 3 yet. Just let's leave it out for now. What would -2 times -7 give us?
+14. +14.
Excellent, excellent. So in essence, this would give us +14. All right, so what I'll be saying is 3 plus 14 for the +14. Okay, now the reason why I did it like this is just to give me a easier chance to understand, what to do with the signs and so forth. So because I see a minus here, I treated it as if it was a negative number multiplied by another negative number. So that's how I ended up with a positive. Okay, so then this case, 3 plus 14, I would get 17. All right, so that is my answer, this particular input. Okay, so I'll give you all some to try for this. I'll give you 4 to try, and then after we'll go into composite functions. This one, our input is 4. So we're going to end up having 4 squared plus 3 times 4. You got that?
Yeah.
Lovely. Now 4 squared is the same as saying 4 times 4. So what is 4 times 4?
16.
16. So then we have 16 plus 4 times 3. What is 4 times 3?
12.
12. So what do we do next now?
Add.
Add. So when we add this, we're going to get what?
28.
28. All right. Make sense?
Yeah.
You follow now, right?
Yeah. Yeah.
All right. So what you did wrong? So this one here, the input was -5. So the important thing is we need to make sure we put this in brackets, okay? -5 squared plus 3 times -5. So the reason why I put this in brackets is very important because -5 squared is the same as saying -5 times -5. And a negative times a negative gives us a positive. So -5 times -5 is +25. Okay, so that's why we had to be careful with. Now we have here now positive 3, plus 3, which is positive, times negative 3. Positive times a negative is a negative, so that would be negative 15. It's important to remember this. So negative times a negative is a positive times a positive is a positive, a negative times a positive is a negative, a positive times a negative is a negative. The same applies for division. So a negative divided by a negative, positive, and so forth. So 25 take away 15 is essentially 10. All right, so for this one, input is 1. So we essentially saying now we put in 1 wherever x is. So 2 times 1 minus 1. So we're saying 2 multiplied by 1, and that's going over x plus 1. So x in this case is 1. 1 plus 1. So then we're left with 2 times 1, take away 1. So 2 times 1 is 2 minus 1 over 1 plus 1, which is 2. So 2 take away 1 is 1 over 2. All right, so that would give us a half. Nice. And about to finish 7?
I got -1.
Lovely. So the things to be careful about with this one was that we have here 3 minus 2 times open brackets 2. So then we would have 3 and then we walk this out. We have to walk out this part first. So this is like saying -2, similar to what we did before, -2 times +2. And a negative times a positive gives us minus. So we're saying minus 2 times 2, which is 4. So we had to walk out this part here first. So then we have 3 take away 4, which is -1. So our answer is -1. All right, let's step up the level now. This time we're looking at composite functions. So composite functions. So we'll have f of x, and we'll say that is equal to 2x plus 1. The next one we'll have is g of x, which is equal to 4x minus 3. Now, the first part for this section that we're going to do is fg5. All right. Now, if you think about this, what this means is that literally we're going to be pretending that this is not here. We are doing this first, and then once we complete this, our answer will go inside of f. So in other words, think of it like this. So we have to put our input inside of f, but before we put that input, we need to work out what the input is. And the input is going to be g5. So first things first, we need to work out what g5 is. So we work out g5. So we look at g, the input is 5. So then we'll have 4. So that's equal to 4 times 5 minus 3. So 4 times 5 is 20 minus 3 is 17. So our output for G5 is 17. So now we could use this 17 as the input for this question. So therefore we could say now F17. So notice we have here FG5. Okay. Now I only put this brackets to show you here how it is conceptualized. But in essence, it would usually be written like this, which simply means that G5 needs to be worked out first and then inserted into F. So we worked out G5 gives us 17. So now we have to say 17 inside of F would give us 2 times 17 plus 1. So therefore I'll have 2 times 17, which is 34 plus 1. And my final answer would be 35. All right. Does that make sense?
Yes.
All right. So let me give y'all one to try now. So you'll try it and then we'll do it together. So G, F, and our input is going to be 1. So let's see how y'all work this out. So remember, from this one, we worked out G5 first. We got our answer, and then our output for that became the input for the other function. So let's see how y'all approach this one, and then we go through it together. Then once we are finished with this, these are some that I want us to go through. So try the first one. Let's go. All right, so with this one here, our input for 1 goes into F first. We need to work that out first. So it goes into this one here first. So that's F1 is equal to 2 times 1 plus 1. So that's going to give us 2 times 1, which is 2. 2 plus 1 is equal to 3. So then now this 3 goes into the G because this is our output for F1. So now that becomes the input for G. So then we would say G input 3 from this here is equal to 4 from here times 3 minus 3. And 4 times 3 is 12. 12 take away 3 is 9. So for this one here, our input is 3. It goes into F first. So then we'll have F3 is equal
Before
to
done it.
2 times 3. So we have 2 times 3 plus 1. So 2 times 3 is 6 plus 1 is 7. So then now I could take this 7 and put it back into F. That's going to be 7, which is equal to 2 times 7, because remember, we're going back into F. 2 times 7, all right, plus 1. So 2 times 7 is 14. 14 plus 1 is equal to 15. So this one here, our answer is 15. And guys, don't let this square here fool you. All this is literally G2. Okay, G2. So of course, we're gonna do G first, input 2. So 4 times 2 minus 3. So that's going to be 4 times 2 is 8. Minus 3 is 5. And then now we put the 5 back into this. So we're going to have 4. 4 times 5 minus 3. 4 times 5 is 20. Minus 3 is equal to 17. Alright, so let me give y'all a little teaser now. Let me see how y'all gonna answer this. Let me see if y'all really thinking about it for this one here now. Let me see what y'all gonna really do if I give y'all this one, right? So this one is gonna be something for you to try before we do a composite function. So I want y'all to try GR. So GR, let's see what y'all gonna get for GR. It's very simple, but let's see how y'all gonna think about it. GR. Let's see what you're gonna do for GR. So this is into our expressions part of the questions.
Are we supposed to know what R is?
Nope.
So we just okay.
I just trying to see how you are gonna process it. It's nothing different to what we did so far in the sense of that we just been substituting. But let me
Right.
see how you would go about doing this.
Okay, alright.
There's a catch to it, right? But we'll get into the catch once you try it.
Okay.
All right. Anybody got it? If our input is R, just like we've been all doing all the time, we just replace this X in this case with R. So therefore we would have 4 times R minus 3, which would give us 4R, because 4 times R is 4R minus 3. Now, because we do not know what R is, we have to leave our answer as this. So therefore,
I got it.
our answer is 4R minus 3. You got that?
Yep.
Nice. So it wasn't that bad, right?
No.
All right. So let's check this out now. So we're going to step it up now. So 6, we are going to say F, G, R. So this is where things get interesting because GR, we do not have a number here. We just have a variable. So we could say the same thing again, starting with GR, because we're doing this first, just like we were doing all the time. So GR is equal to, we replace the X with R, so we'll have 4 times R minus 3. So therefore, 4 times R is 4R minus 3. Now, this here is our output for GR. So our output for GR is 4R minus 3. Our output for GR is 4R minus 3. Therefore, this would become our new input for F. So our input for F would be 4R minus 3. Okay, so notice we're not doing anything different to what we did earlier. Literally, we're just taking our answer and putting it as the input for this one. So now, everywhere where I see X in this F, I will replace it with 4R minus 3. Okay, so just to highlight the concept, let's do it like this. This here in blue is my input, and for the function F, what I'm saying is everywhere I have X, I'll replace it with 4R minus 3. So let's just say we had the X here. So I'm just writing the equation right here for you to see. So 2, or maybe I should put it here. So 2, let's just put it here, maybe over this. So 2 X plus 3. So let's just highlight the X now so you could see what we need to change. So if you look at this, literally where you see this X, we're replacing it with this here, 4R minus 3. So I have on color coded. So 4R minus 3 is going to substitute in for this X. So then therefore we would have 2 Now this x has to go with 4r minus 3, so 4r minus 3, then we could say plus 1. So notice what I did there. I literally substituted the x with 4r minus 3. So as you can see here, this here is almost the same as saying 2x plus 1. Okay, this x is just covering the 4r minus 3 because that's the input. Now, all I have to do is simplify. So I have to say 2 times 4r, then 2 times minus 3. So that would give me 2 times 4r is 8r, and then 2 times minus 3 is minus 6. Okay, so I'm still looking at this as a positive multiplied by a negative. So 2 times minus 3 is minus 6. And then I can't forget my plus 1 over here. So therefore, it would be equal to 8r. And because two of these are like terms, so they don't have any letters on them, they are like terms, I can say minus 6 plus 1 is minus 5. So my answer here is 8r minus 5. And that's it. Now, the same principle, if I was to try it with just leaving an expression, I want an expression in terms of x. So fg x. So just like I had it here with putting in r, I would just use x instead, because sometimes you're given the question like this to find an expression. And why we call it an expression is because we end up getting it like this. It's not an actual answer, it's an algebraic expression. So before, when we was doing this, as you can see, we got actual answers. So the answer for this was 35, the answer for this was 9, the answer for this was 15, and the answer for this was 17. Now for this here, we end up getting the answer for this is 4r minus 3, which is an algebraic expression, and the answer for this was 8r minus 5, which is also an algebraic expression. So let's see what y'all will get for this here, and then for 8g f of x. Let's see what y'all would get for that. So we use these two processes here to kind of show you what is actually happening when you put an input. So we use an input that is not the x, just so you could see. Now with the x being the input, it's going to be the same principle. So let's see how y'all do this. So essentially, you should get the same answer as this, but instead of 8r minus 5, you should get 8x minus 5. All right, so I want y'all to work on this one, and let's see what you get.
Teacher, I got 8x.
Excellent, lovely. So this one is the same concept. So we generally have, like we were saying, x is the input. So then we have 4 times x minus 3. So therefore we'll have 4x minus 3. Then now this is the output for gx, which is essentially the formula. And then we put it inside of f now. So 4x minus 3, and that will be equal to 2. So we substitute this x with the output of gx. So then we'll have 2 open brackets 4x minus 3 plus 1. So then when we work that out, we'll have 2 times 4x, which is 8x, and 2 times minus 3 minus 6 plus 1. So therefore we'll have 8x minus 6 plus 1 minus 5. So answer is 8x minus 5. So let's see what y'all get for gf of x. Y'all doing good, man. Y'all doing good. You got the last one yet?
I got 8x plus 1.
8x plus 1. Sounds about right. Now that we have the fx part that we're trying to find, remember the input is x. So we are saying that f, the input is x, and that's going inside of the input, which is gonna go inside of here. So it's gonna be 2 times x, which is essentially the input for this. Then we're gonna say plus 1. So then we're gonna say 2 times x is 2x plus 1. So that's basically our output for this. All right, that's basically our output. So then the next phase is we'll take this output and put it inside of g. So then we have g 2x plus 1. That's the input. Now that has to go inside of this x here. So wherever this x is, we replace it with 2x plus 1. So for instance, I would say 4, which is this 4. Now my x would have been where these brackets are, but instead of putting x, I'll put this input here, which is 2x plus 1. And then we say minus 3. So then now I have to multiply out. So then I'll go 4 times 2x, and then after 4 times 1, so then we have 4 times 2x is basically 8x, and then 4 times 1 is 4 minus 3. So then we have 8x, And then 4 minus 3 is basically 1. So 8x plus 1 is our final answer. All right, so that's how you have to do it. So you just have to go through all the stuff that we went through, take it step by step, pause it as you go along, see what you see, understand it, try it for yourself, and then after, you just go with it, you just go with it. Keep practicing. The practice is what's going to make this solidify.